Good morning, students. Today we are moving to the second lecture of the first module, Oscillations and Waves. We are going to discuss the solution of differential equation of a damped harmonic oscillator. In the first lecture, we derived the differential equation of a damped harmonic oscillator. So today we are moving to the solution part. So, as we have seen in the last class, the differential equation of a damped harmonic oscillator is d square x by dt square plus 2k dx by dt plus omega square x is equal to 0. So, it's a solution, it's a second degree differential equation in x, and we are assuming that the solution of this second order differential equation in x is of the form x is equal to a e raised to alpha t. There are a number of methods to derive or to find out the solution of the differential equations, and this is one of the methods. So we are assuming that the solution will be of the form x is equal to a e raised to alpha t, and where a and alpha are two constants. Now differentiate this equation 1 with respect to t. So what we are getting is dx by dt. So we have dx by dt is equal to a alpha e raised to alpha t. Now differentiating this equation once again, we have d square x by dt square is equal to a alpha square e raised to alpha t. So now we have x dx by dt and d square x by dt square. Then substitute these values in the first equation, that is the differential equation of the damped harmonic oscillator, equation number A. So after substitution we have a alpha square e raised to alpha t plus 2k a alpha e raised to alpha t plus omega square a e raised to alpha t is equal to 0. Take the common factors outside, that is a e raised to alpha t into alpha square plus 2k alpha plus omega square is equal to 0. Now in this equation, we know that if x into y is equal to 0, either x is equal to 0 or y is equal to 0, or both x and y can be equal to 0. But here in this equation, a e raised to alpha t is not equal to 0. So the only possibility is that the term inside the bracket is equal to 0. It's a quadratic equation in alpha. So to find the solution of this equation, we have the general form of the equation, what, minus b. Okay, so we will have the solution of this equation as alpha is equal to minus 2k plus or minus root of 4k square minus 4 omega square divided by 2. Or dividing each and every term of this equation with 2, we have alpha is equal to minus k plus or minus root of k square minus omega square. Now we assume that the solution of the differential equation of damped harmonic oscillator is of the form x is equal to a e raised to alpha t. Now we have the alpha values as minus k plus root of k square minus omega square and minus k minus root of k square minus omega square. So I am writing the general solution of the differential equation of the damped harmonic oscillator as x is equal to a constant a1 into e raised to minus k plus root of k square minus omega square into t plus a2 e raised to minus k minus root of k square minus omega square into t, where a1 and a2 are two arbitrary constants. So the nature of oscillations represented by the above equation depends on the relative values of k and omega. Okay, now based on the values of k and omega, we have three different cases. The first case is heavy damping or over damped condition. That is when k is greater than omega. Now case 2, critical damping. K is equal to omega. Then case 3 is light damping or under damped condition when k is less than omega. We know that k is the damping coefficient and omega is the natural frequency of oscillation. Okay, so let us see the first case. Case 1, heavy damping condition or over-damped condition when k is greater than omega. So in the general solution, we have x is equal to a1 e raised to minus k plus root of k square minus omega square into t plus a2 e raised to minus k minus root of k square minus omega square into t. There is no k here. Okay. So in this equation, if k is greater than omega, we know that k square minus omega square is a positive value and therefore root of k square minus omega square is real. And root of k square minus omega square is less than k. So if we are putting these conditions in the general solution, we know that minus k plus root of k square minus omega square minus k plus a small value. So the result will be negative. And minus k minus root of k square minus omega square. As root of k square minus omega square is a real quantity, we have this term is also negative. Both these terms will be negative. So x is equal to a1 e raised to minus of some value into t plus a2 into e raised to minus of some parameter constant into t. That means both these terms in the exponential decreases exponentially to 0 with respect to time without performing any oscillations. And this type of oscillations are called over-damped condition or heavy damping condition. So if we plot the displacement versus time graph, then we can see that there will not be any oscillations. The displacement decreases from a constant value. It decreases exponentially to 0. Okay, I will show you the plots after discussing the three cases. Now case 2, that is the critical damping condition. Critical damping condition when k is equal to omega. K is equal to omega, we have k square minus omega square will be 0, that is equal to 0. So while we are putting this case k is equal to omega condition in the general solution of the differential equation, we have x is equal to a1 e raised to minus k plus 0 into t plus a2 e raised to minus k plus 0 into t. Okay, so we can take e raised to minus kt as a common factor. So we have x is equal to a1 plus a2 into e raised to minus kt. This a1 and a2 are two arbitrary constants. That means x is equal to some constant into e raised to minus kt. So here also it indicates that if you plot the displacement versus time graph, here also the displacement decreases exponentially to 0 with time without performing any oscillation. So this is also a non-oscillatory motion or aperiodic. Okay. Now an example for the over-damped condition is an oscillator that oscillates in a highly viscous medium like oil or water. There, without performing any oscillations, the displacement or the amplitude decreases exponentially with time to 0. Okay. Here also in the critical damping case condition, example is ballistic galvanometer. The pointer moves quickly to the correct position without performing any oscillations. Now we are moving to the third case, that is light damping or underdamped condition. In underdamped condition, k is less than omega. When k is less than omega, k square minus omega square is negative. Or root of k square minus omega square will be imaginary. Okay. So while I am writing root of k square minus omega square, I am putting this k square minus omega square as a constant, say beta. I am taking k square minus omega square as some constant. I am taking this omega square minus k square as a constant beta. So I am writing this as plus or minus I beta, where I is root of minus 1 and beta is root of omega square minus k square. So from our general solution of the differential equation, we have x is equal to a1 e raised to minus k plus I beta into t plus a2 e raised to minus k minus I beta into t. Okay, now look at this equation. Here again, e raised to minus kt is a common factor. So I am taking this e raised to minus kt outside, and inside the bracket we can write a1 e raised to I beta t plus a2 e raised to minus I beta t. Now, we have the general equation e raised to I theta is cos theta plus I sin theta, and if it is e raised to minus I theta, cos theta minus I sin theta. So here we are going to expand e raised to I beta t as cos beta t plus I sin beta t, and e raised to minus I beta t as cos beta t minus I sin beta t. So in the next line we have x is equal to e raised to minus kt into a1 inside the bracket expand e raised to I beta t as cos beta t plus I sin beta t plus a2 into cos beta t minus I sin beta t. Okay, now here again we can take the coefficients of cos beta t can be taken outside. So I have from the first term the coefficient of cos beta t as a1, and from the third term it is plus a2. So in the next equation we can write like that: x is equal to e raised to minus kt into a1 plus a2 into cos beta t plus I into a1 minus a2 into sin beta t. Okay, now in the next line, see this, we are putting a1 plus a2 as a sin phi and I into a1 minus a2 as a cos phi. So we can write the solution as x is equal to a sin phi cos beta t plus a cos phi sin beta t. Okay, or x is equal to e raised to minus kt into, see this is nothing but here a can be taken outside, then inside the bracket we have sin phi cos beta t plus cos phi sin beta t. It is of the form sin beta t plus phi. We know that sin a plus b is sin a cos b plus cos a sin b. So now we are getting the solution of the underdamped condition as x is equal to a e raised to minus kt into sin beta t plus phi. This equation represents the simple harmonic motion with amplitude a e raised to minus kt and time period t is equal to 2 pi by beta. We know that beta is root of omega square minus k square. So we can write it as t is equal to 2 pi by root of omega square minus k square. So now if we are looking at this equation, we know that the amplitude of oscillation decreases exponentially with time by performing some oscillations. Okay, so if we plot the displacement versus time graph, in the case of this underdamped condition, we are getting a curve like this. So this is only the oscillatory motion, the underdamped condition or light damping. There we are having an oscillatory motion. Now consider the case of overdamped condition. Overdamped condition, as I said earlier, the amplitude of oscillation decreases exponentially with time but without performing any oscillation. This is the overdamped condition. Then critically damped condition, there also amplitude of oscillation decreases exponentially with the time and it is much faster than the overdamped condition. We have x is equal to some constant into e raised to minus kt in the case of critical damping. So it is much faster than the overdamped condition. So the red curve, red line, solid line, it indicates the critical damped condition. It is much faster than the overdamped condition. Overdamping also without performing any oscillation, the amplitude of oscillation or the displacement decreases with time. Okay, so this is all about the solution of the damped harmonic oscillator. It's a very important topic. It used to ask for the university examinations. So all have to learn the differential equation of a damped harmonic oscillator and its solution. And you have to write it in your notebook. Okay, thank you.